Today, section 6.3, we want to be able to write equivalent forms of exponential and logarithmic equations, be able to go back and forth. If I give you exponential, you give me logarithmic. If I give you logarithmic, you should be able to give me exponential. And then use some of our properties to help us solve equations and the definitions of just writing logarithmic and exponential equations. So let's get started. First question would be, what is a logarithmic? Or, in short, what is a log? You're going to see LOG is our phrase we use for what is a logarithm. Now, logarithm, what is a logarithmic equation? Those are things you will see here along the way. I think if you check the dictionary, since this is a new word for most of us, it will say something to the effect of or pertaining to the exponent. So we've been dealing with exponential equations, and now we're going to switch it up and say, well, what do you do to get the logarithmic version? Now, in essence, we learn that a logarithmic is the inverse. So let's go ahead and see what happens here. We know a lot of things going on here on this page. If we start up here, we've got our equation, our generic equation, y equals ab to the x for all exponential equations. So we also have this basic exponential equation, y equals 10 to the x. And let's do a little quick xy table here and graph that to see what we're really talking about. So we did a few negatives, a few positives, and 0. So in our first equation here, when y equals 10 to the x power, let's start with the 2. If x is 2, 10 to the second is 100, so y is 100. When x is 1, 10 to the first is 10, so y is 10. When x is 0, 10 to the 0 power is 1, so y is 1. When x is negative 1, that means 10 to the negative first power, we learned is not an exponent, or excuse me, not a negative number. It means a reciprocal action, so flip me, so it would become 1 over 10. If you'd like to write the decimal, 0.1, go ahead. And so the negative 2 would be the same sort of thing. It would be 1 over 1/100th, or 0.01 if you prefer that. So when we come to our graph here, I'm obviously not going to be able to get all of those on, but we're going to get a good representation. So let's go. If I'm at negative 2 on our graph here, we're at 1/100th, which we know is very, very small. So I'm going to try to put this as close to that x-axis as I can. If I do negative 1, I'm just up slightly. So I can't hardly move this point because the space is so small, but we'll get it. And we go to 0 and 1, and I counted by 2's here, so 0, 1 puts me like right in the middle here. If I go over to 1, I'm supposed to be up at 10, so very quickly 1 puts me at 10. And then if I did 2, you can see we don't get 100 on this, but it's even going to be higher. So if we try to graph this, I'm looking at something that's coming very high. Make sure we go through our point here, and our 0, 1 point, it comes down, hugs this x-axis out here in the negative range, and I'm just going to put zeros on both ends. So there is our example of our exponential curve that we've been talking about. Of course, the x-axis in this case would be the asymptote, right? The domain and range, if we look at the domain first, all x values I've graphed positive, negative, zeros, fractions, decimals, they're all there. The range is definitely positive reals. We have not one negative, and nor do we have 0, because we have not touched or hit, crossed that x-axis in any way, shape, or form. Is this a function? Well, sure. Do your vertical line test, running eyeballs of vertical lines through this. None of those vertical lines ever get hit by more than 1 point. So yes, it is a function. Now, that's the general basic exponential equation. If we said, well, I want to graph the inverse of that, then our basic definition of inverse is flip-flop x and y. So I have here x equals 10 to the y power. But we have a slight problem because if you try to graph that, even just put it into your grapher, we always like the idea of y equals. And we don't have y by itself, and we don't know what the power is, so it's like, how can you undo that y power when you don't know what it is? So we're sort of stuck. We have a little issue. But we do have another definition for inverse, which says flip-flop x and y. So if we would take those same ordered pairs that we have over here now and flip-flop them, so we would get our xy combinations, then we could have an idea of what this graph does. So let's go. If I'm out here at 100, which is obviously off my graph here, I'm only up at 2, and 2 is that first line. So let's go. 10 would be the next number, so if I'm out at 10, I'm a 1. There's my approximate point. If I'm at 1, which is halfway, I'm at 0. Notice that is on the x-axis there. If I'm at the number 1/10 for x, I'm down at -1, which is halfway. 1/10 is very, very close, so let's just get it close to that axis. And then if I'm at 1/100th, which is even smaller, tighter to that axis, I'm down at -2. And -2 is only one marking. So we're getting closer and closer. So our curve is very similar to what we saw a minute ago. Let me graph it here. It's hugging this time. I probably should have done that a little closer. It appears to be hugging the y-axis with our curve hitting here and coming up. Whoops. Should have been really super tight because out at 100 here it's only 2. Okay, so I didn't draw that very well, but you get the idea. So every point that was an x becomes a y, every point that was a y becomes an x. So that is the inverse. So when we write it like this equation represents the inverse equation, but that's not something that's acceptable. So this is the same thing that happened to our great researchers and mathematicians early on, and so they said, you know what, we have to come up with a way to do this. And so they came up with the idea of logarithms, common logarithm. These are all based on base 10. We could really do this with other base numbers too, but since base 10 is our decimal system, we're used to it, so that's why another reason I use this example. All right, so let's go and check what x equals 10 to the y. That's the equation we're working with right now. So if we do x equals 10 to the y, compare that. That's our inverse equation. Compare that to this statement. Y equals the log of the number x in base 10 if and only if 10 to the y equals x. Well, there's our equation, 10 to the y equals x. So we're saying that these mathematicians have come up with this logarithmic function. Now notice, I like to say there are things that are all on the same level here. The 10 really is a subscript. It might even be better to look at it like that. The y, the log, and the x are all on the same line. The 10 is not. Okay, so if we go back and I just write that, we would look maybe at the top of everything rather than the bottom. But if we're talking about lining things up, the y, the log, and the x are all on the same line. The 10 is the subscript. So think about how I read that again. I said y equals the log of x, reading everything on the same level first, in base 10. Now here's a couple other choices. Y is the log of x to the base 10. Y is the log of x in base 10. I believe that's what I said. And you can also say y is the exponent of the number x when you're in base 10. That might be one of the more simpler ways right now to think of it because you're really not used to this log idea and what logarithmic means. So y is the exponent of the number x, or for the number x, if we're in that base number, in this case, base 10. So look at these two examples. You definitely know now that 10 to the second equals 100. So look what that same exponential equation looks like in logarithmic form. And this 2 really could be on either side. So if I wanted, I could have written this as the log of 100 in base 10 also equals 2. And that may make more sense for some of your brains. But it does read the log of 100 in base 10 equals 2. If you like one of the other methods, I might say the exponent for the number 100, if I'm in base 10, is 2. So there's nothing missing. These are true equations. Everything's there. But this is how you have to get used to and be able to go back and forth from what we call exponential form to logarithmic form. There is one other quick equation we can give you. If you're looking at two exponentials and they truly are equal, and it doesn't even have to be base 10. So let's jump out of the box and let's say 2 to the third equals 2 to the y plus 1. Let's just do something like that. We're comparing two numbers that have the same bases. That's what's key on this. So if you look at the property, you must have the same base to apply this property. So then they're saying if the bases are the same, then you know the exponents have to be equal. So if we're in base 2, then we know the 3 has to equal the y plus 1. And so you can look at that and think about it, some of you in your head, and you can say, oh, okay, that means the 3 has to equal the y plus 1. So that means the y has to be a value of 2, because 2 plus 1 would give me a 3. That is called the one-to-one property, and it's something we're going to be using in this chapter on and off to help us simplify some of our equations. So another good thing to put in your notes. Okay, let's move forward and see what kind of problems. Here's one, and we'll save a few of these for class, but write each of the following in logarithmic form. So on your notes, please, 10 squared equals 100. And we already had that on the other slide. If you don't go back, let's try to rewrite it. So what I want you to do is I want you to take this stuff at the top, and I want you to use it in your log equation. So let's see. If 10 squared equals 100, that would mean, and decide how you're going to say it. Are you going to say it log, or are you going to say exponent? The log or the exponent of the number, I think I'm going to grab a 100. Put it on the same level. In base, what base am I in? Well, base over there is a 10. And I do have a 10 way down here. So let's put it down here. And let's make sure it's a subscript and everybody sees that it's subscript. And then I'd have my equals. And then we'd have our answer. So the exponent for the number 100, if I'm in base 10, is 2. So I'm saying that would be my equation, my rewritten version of the exponential equation in logarithmic form. Okay? So I'm going to reveal some others, and I would like you to rewrite them on your paper so that we can discuss them when you come to class. They all work the same way. There are no exceptions. Some of the exponential equations that you're looking at here on the left are fairly basic ones you should know, recognize. But if you don't, like here, maybe if you don't know your negatives very well, they work the same way. Here's one where it's not even written in exponential form, so you need to think about what the exponential form would be, or rewrite it. That would be another choice. And then write it in log form. Okay? So we're looking for you to fill in the blank on the last three. Okay? Next. Now let's go the other way. What if I give it to you in log form? You had better be able to write it in exponential form. Now on this one, instead of me just pulling the answers from the top this time, I'm going to show you where things come from. So we know we're going to exponential. So we know b to the x equals a number. We need some number to a power equals. So if we do that, reading it, the exponent for the number 100 in base 10 equals 2. Everything is there. So all we have to do is rewrite it in exponential form. So most of you know the base, whoa, I didn't want that to happen. I thought I could take the individual numbers. So let's just hit reset here. Put it back to where it was, and I'll take them from up top. I thought I could take them out of there. So let's go. What I say, my base number was 10 to the power of 2 has to equal, can't steal an equal sign, can I? Nope, so we'll just write it. Equals, and what's the number I can steal? Well, it has to be the answer, which we know is 100. So go ahead and also rewrite these 3 log form equations in exponential form. Now notice there's nothing missing other than approximately equal to sign down here. I don't know where it went, but let's put it back in. We got our approximately equal to. So the log of 1.78 is approximately, in base 10, is approximately equal to the number 1/4. So that's what you would use there. Obviously that one, it's not a whole power, so it's probably decimal, so that's why the approximately is there. So rewrite those, add those to your notes, and we will check those when we come to class. Okay, if you had to evaluate a log without a calculator, we could text your answer in, we could write your answer in here. We're just going to write a few of them, and then I want you to share or be ready to share in class. So there is a piece missing. You're going to say, well, wait a minute, these are different because they don't have the equal to on them, and you're right. So if they don't have the equal to, you have to find that value. So I'm going to read these just slightly different this time. I would say the log of the number 100 in base 10 is what? I don't have it here. I could say the exponent for the number 100 in base 10 is what number? So as I say that, we're writing either in your brain or on paper. You're saying, okay, this is log form, so I know I have to be writing in exponential form. So find the base. 10 to the what power, because that's what's missing, has to equal 100. So then all you have to do is say, oh, what power? And replace that question mark with, in this case, a 2. So go ahead and do the remaining 3. Jot those on your paper, and we will discuss those in class as examples to see if you really did understand how you change from log form to exponential form, and in this case, when there is a piece of the statement missing. That's the difference. Now, you'll notice I've got, this is the first part of 6.3, and we will be spending a couple days on it. So if you don't have time tonight, go ahead and turn the video off at this point. I'm going to continue on and use the next part, which will be for our second day's assignment. But I think it's not that far. It uses some real life situations. So here we go into that portion of the video. All right, if I would say I want you to take an equation that is in log form and solve it, you should be able to. But in this case, we know that when we were writing all these, we had 3 numbers. And right now, some of you are looking at it and say, you only have 1 number here. So here's something that's just a basic fact of logarithms that you aren't familiar with yet. But if we are talking about common logarithms, which was anything in base 10. So if I'm a common logarithm, I am in base 10. Okay? So if we're in base 10, everybody says, well, we know we're in base 10, so why write it? So anytime you see, like on this one, a logarithm setup, and you do not see a subscript, you can, from here on, assume that we are in base 10. If you like to see it and write it, then you could put your little 10 down below there, but you don't have to. Okay? So let's reset this and say that's what it's going to look like from the beginning. And so now my brain has to go through and say, well, gee, I'm looking for the log or the exponent. Remember, that's how we read it, so it makes sense to our brain. What is the exponent for the number x if I'm in base 10? And it says, what is? Well, that number's there this time. The 3.5 represents it. So how about this? The exponent for the number x in base 10 is 3.5. Well, for most people's brains, that means 10 to the power of 3.5 is x. Now, granted, you cannot do that in your head, but if you went to your calculator and did 10 to the 3.5 power, you would get your answer that you need here, and it would definitely be not one of those powers of 10. And we would have to approximate it. So 10 to the power of 3.5, in this case, 3,162, and I'm going to just say 0.3-ish. 3,162.3-ish. Just done on the regular screen. That's just a powering key. Okay? So if we say log of an unknown number, and there's no subscript, reminder, that means base 10, and then you can put your exponent right on, and we're not expecting you to be able to do powers of non-whole numbers, tens, or any other numbers in your head. So that's when you are going to have to use some of your technology. Now I'd like to quickly change to our calculator here. Let's see how this works. And our calculator's sitting here, and if we would turn this calculator on. Guess it's not going to work as well as I wanted. So if we go back here to our page, and you can use your calculator without it, if I would say, what's the log of 50? Okay, so you know we're looking for an exponent in base 10 that gets us as close to as we can to 50. Well, just off the top of your head, no calculator please, you should know 10 to the first, 10 to the second, 10 to the third, you know, in our powers of 10. Because we know this is power of 10 because we don't have our subscript there, which represents our base. So we know we're in base 10. But we know 10 to the first is 10. We know 10 to the second is 100. So we know right now that the answer to the log of 50, the answer we're looking for, has to be a number between 1 and 2 in terms of our powers. The exponent has to be a number between 1 and 2. We're not expecting you to know that in your head, but if you go to your calculator, you do have a log key. It's over there on the left-hand side, so find it. And if you hit log, it should put the log right on the screen. Some calculators will also put a parenthesis. And so right after that, you can put your number in. In this case, it's a 50. So the log of 50 equals, hit enter, and you get the calculator to spit out that number that represents what you're looking for, which you already know is between 1 and 2, but the calculator then does the math that goes with it. So 1.698-ish, so we'd be looking at, it's approximately a 1.7-ish. So if you have the log of a number, and it's not one of our powers of 10 that you recognize, you could use your technology to help you get to where we need to be. Okay, so from there, if we talk about real life situations, logarithms happen all the time. Actually, logarithmic scales happen in 3 things we're going to be discussing in this section. The pH, which a lot of you have done in your chemistry classes already. pH is a logarithmic scale. You can see it down there with my color number line. The decibel system and the Richter scale. Decibel for sound, Richter for earthquakes, tremors. So most of you know that the pH scale, since it's here, goes from a low number of 0 to a highest number of 14. being very strong alkaline base, some people would call it, versus the zero end are your acids. So you should be able to answer some questions about those. Now, I'm going to, I believe on my next slide, show you some equations. No, we're going to talk about logarithmic and linear scales. The equations will come on the next slide. The difference. If I say I'm in the pH scale or the decibel scale or the Richter or any other logarithmic scale, I want you to look. When we've been doing our work previously, we were mostly working on a linear scale. So look down below. 10, 20, 30, 40, 50. Those happen to be the intervals I've chosen for this linear scale. And you would say, well, they all go up by 10. I'm going up by 10. It's that constant difference, we like to call it. All right, and all the way through it goes up by 10. It doesn't matter how big or how small I am on my left or right on my scale. Everything's by 10. So that's that constant difference, that slope, we like to sort of say, was our definition. But now take a look. What happens when we're on the logarithmic scale? The logarithmic scale, if I mounted a whole new set of numbers, you can see if I'm in a log, which pertains to the exponent, the first tick mark would have to be 10 to the first. The second one would have to be 10 to the second, 10 to the third. We'd be counting by powers. Now look back, because if we take those off and start saying, well, let's start talking about the intervals in those spans. Well, we know 10 to the first is 10, and 10 to the second is 100. So 100 take away 10, that's an interval of 90, just looking at those two. Now we're at 100, and the next 10 to the third is 1,000. 1,000 take 100. And you can see that we have uneven, definite difference, non-constant, all those are good choices, in all of our works, or all of our intervals. 10 to the fourth would be now 10,000. 10,000 take away 1,000 gives you 9,000. And the pattern that's established, the next one, yes, is going to be a difference of 90,000. Then 900,000. So these things are going up. The difference on these, they're going up very, very fast compared to our linear scale. So the difference is logarithmic is that it change exponentially going up versus the other one is that constant difference. So in working with these three scales, you should be able to work with a few situations. So let's look. Sound intensity is usually measured in watts per meter squared. You can hear usually a range of noises between 10 to the second and 10 to the 12th sound intensity, and an increase of any number n decibels multiplies the intensity by 10 to the n divided by 10 power. So, example there. If I said I have one sound that measures 10 to the 5th, I have another sound that measures 10 to the 7th in terms of sound intensity, then you should be able to tell me 10 to the 5th and 10 to the 7th is a difference of 2 powers of 10. But 2 powers of 10 we know is 10 to the 100th, or sorry, 10 to the second is 100. So we would say the one sound to the other would be 100 times more intense than the other. So that's an example. Here's one conversion you can use depending upon what they give you. Is the answer in decibels, D, or is it in sound intensity, N? It's not one you have to memorize, but it is one that you could use in your work today. Richter scale, same thing, another logarithmic scale. You usually use the Richter scale in earthquake, measuring movement intensity of the earthquake. So again, if we have an earthquake that's 7.5 compared to an earthquake that's 4.0, which both of them are quite intense, you can say, wait, that's a difference of 3.5 So the 1 is only 3.5 times as intense? No, these are logarithmic scales. It would be 10 to the 3.5 power. We know 10 to the third is 1,000, so 10 to the 3.5 power would be approximately 3,162-ish. So 3,162 times more intense than the other. That's a big difference comparing the 3.5 to what it actually is in terms of intensity. And pH scale, that's again in terms of intensity of the severity of the acidity versus alkalinity of the substance. And most of you know that the pH of a substance is equal to the negative log of the positive hydrogen ion concentration. Okay, with that, you have the real world stuff that goes with the second day, and I think you're set. And if you have questions, and make sure you bring those extra problems that we discussed in your notes to class, we should be good to go for exponentials and logarithms.